Wow, that was maybe some of the hardest stuff to read in this book so far out loud. This book, Differential Geometry, is dedicated to Professor Stefan Bergman. Kernel Function and Conformal Mapping by Stefan Bergman. It is not dedicated to Erwin Kreyszig. Salut tout le monde. Welcome back to another Differential Geometry reading stream. I'm Anthony, obviously, and we are reading Differential Geometry by Erwin Kreyszig. We are hopefully going to read two sections today. Section 63 on isotropic lines and isothermal coordinates, and section 64 on the so-called Bergman metric. Section 64 is maybe one of the hardest hitting sections in this book so far. I definitely had to pre-read some of this stuff in order to make sure that I pronounce everything correctly. But furthermore, you don't see this in the PDF copy of the book, but this book, Differential Geometry, is dedicated to Professor Stefan Bergman because I guess this is the backstory. So Erwin Kreyszig was born January 6, 1922 in Germany. And so he spent his youth, grew up getting his PhD and so on and so forth in Germany. Now, a little bit earlier than him, there was Stefan Bergman. So Stefan Bergman was a little bit older. He was born May 5th, 1895, and he is originally from Poland, but you can imagine that as he was, coming of age, getting his PhD and stuff, and also Stefan Bergman is Jewish, so imagine being Jewish living in Poland, in the early 1900s is a recipe for some problems. So he moved, Stefan Bergman, that is, to Russia, then to Paris, then I guess to the United States. And so the long of the short of it is that Stefan Bergman was at Stanford starting in 1952. So our boy Erwin Kreyszig was in Germany. He's getting his PhD, all that stuff. And it turns out Erwin Kreyszig, his background was originally physics. And then as he was specializing in math, he was really more into complex analysis. But then he gets his PhD and he goes to this place that's working on complex manifolds of several variables. And I guess it's that was like the early 1950s, so like 1952, 1953. That is basically the basis of this book, Differential Geometry, because then Erwin Kreyszig goes to Stanford in 1954. So keep in mind, Stefan Bergman, he's a little bit older than Erwin Kreyszig at the time, gets to Stanford in 1952. Okay, now Kreyszig is at Stanford 1954. And at the time, this was like a hot spot for analysis. So makes sense with Kreyszig being a complex analysis guy. And with Bergman being a little bit older, having a little more experience, a little more clout, Kreyszig under him then does some work and stuff and blah, 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 it goes on. But then you could imagine that the time period right before where he was doing, Kreyszig that is doing stuff with vaguely differential geometry concepts. Then he goes to Stanford and he's working with guys like Bergman doing this complex analysis stuff. Okay, now in this book, which Kreyszig dedicates to Bergman, now we're in section 64, the Bergman metric, where we've got like the cross section of differential geometry and complex analysis and functional analysis. So yeah, this is a pretty hard-hitting book. And interestingly enough, Bergman died in 1977 at the age of 82, and Kreyszig died December 12th, 2008, at the age of 86. So this coming January, he would be, what, 103 years old? So pretty interesting. In the spirit of how a lot of these other episodes have gone, I'm going to read from Wikipedia to start things off. You could probably get a lot, if not more, than what you might expect from the book, simply just from looking up on Wikipedia first what the sections in the book are going to be about. So, all right, so I've kind of touched on it before. In math analysis, I'm not talking about data analysis where it's like you did some experiment and now you need to analyze the data and you call the act of doing that your analysis. That's not the analysis I'm talking about here. In math, analysis is a branch that what I would say is basically just doing calculus, but rigorously with proofs. And that's the way that you go from like a simple Newtonian 1D look of calculus to doing things like systems of partial differential equations with complex variables, let's say, right? That's what that whole branch of math is all about. And there are the main pillars within that branch, you could say, of real and complex analysis, functional analysis, and probably like measure theory, I would say. I haven't really touched on a lot of stuff like measure theory, Lebesgue integration in a lot of these videos. Kind of comes up though in the other big pillar, which is kind of really involved in what we're going to read in differential geometry. That's functional analysis. Okay, so the recap of real and complex analysis is you're doing calculus, right? So derivatives, integrals of functions. So a take I have of functional analysis is that you're just going to do it all meta now, where instead of the space has numbers in them, the space has functions in them. Okay, so it's, another layer of abstraction. You'll see what I mean here. We're reading from Wikipedia. Functional analysis is a branch of mathematical analysis, the core of which is formed by the study of vector spaces endowed with some kind of limit-related structure. For example, inner product, norm, or topology, and the linear functions defined on these spaces and suitably respecting these structures. So the big examples of these are the normed vector spaces, namely Hilbert spaces and Banach spaces. And honestly, I've got in front of me here like 8 pages of notes, I think. Let me count this real quick. 8 pages of notes. And I think there's only 6 pages of reading in the book. Because there's a lot that could be said as far as like background to a lot of the things that are brought up in these sections, that it's kind of just like taken for granted that if you're just going to, read this on YouTube for a mass audience, who knows what you, the audience member, do or don't know. Anyways, so a Hilbert space, named after the prolific mathematician David Hilbert, is what you would call a complete inner product space. So a Hilbert space is essentially a vector space equipped with an inner product that allows for notions of distance and angle similar to what we have in Euclidean space, but in possibly infinite dimensions. And like I said, we could have functions inside of these bad boys. So if we have a Hilbert space H, let's say, then H is a vector space, and on H we also have defined an inner product, which is a function, which is a Cartesian product onto real numbers or the complex plane, which assigns to each pair of vectors x and y, which are the inputs that you're taking, namely it's a Cartesian product, but that's just a way of classifying the function. an inner product anyways. You take these vectors, x and y, which are input, and these vectors, of course, are members of your Hilbert space H, and you get a scalar which satisfies the following three properties. We have linearity, symmetry, and it's positive definite. I'm not going to spell those out for you guys because I'm sure that you're smart enough that if you don't already know what those things are, you could look them up, or you already know them. That's great. You probably, if anything, you know more than what I already know about these things, that you're just like, you've already skipped ahead to reading from the book. I don't know. But furthermore, on this Hilbert space H, we also have a norm defined, and you can also have a metric defined. So that's one of the main spaces that are involved in the study of functional analysis. Okay, we call them Hilbert spaces. And look up that guy, David Hilbert. When you look up the biographies of Erwin Kreyszig and Stefan Bergman, the people that are, the who's who involved in who they're all collaborating with as they're jumping around to all these big name universities, they'll often describe these people's clout in reference to David Hilbert. Because I think David Hilbert was on the scene and he was, like coming up with all these results. And then there was this, huge, like exhaust, maybe that's not the right word, of PhD students and stuff that came after him. And anyways, big dog David Hilbert. But we also have in functional analysis the so-called Banach spaces, B-A-N-A-C-H, after Stefan Banach, where a Banach space, it's kind of similar to a Hilbert space. A Banach space is a complete normed vector space where, unlike Hilbert spaces, Banach spaces are defined solely by a norm, and they do not require an inner product. So, for a Banach space, let's say call it B, we have that B is a vector space over the real numbers or the complex plane. And we also have for B a norm, which is a function from B to the real numbers, let's say, which satisfies being positive definite. It obeys scalar multiplication, and it is subject to the triangle inequality. Furthermore, the space B is complete, where, like Hilbert spaces, Banach spaces are complete under the metric induced by the norm D between elements x and y of the Banach space is equal to the norm of x minus y. So this guy Banach, his name is also lended to what's known as the Banach fixed point theorem, which, to kind of like bring in more concepts to show that whatever these guys, I'm going to bring up a lot of names of mathematicians here in these 8 pages of notes or whatever, to kind of show that these guys who were all really fleshing out complex analysis, PDEs, all that theory involved, we're kind of all just like working on the same stuff, and then after the fact we're looking back at it and we're like, okay, this is how you solve PDEs and you do complex analysis, guys, and then it's just like got all of their names just like thrown all over everything. So it's like, okay, we had Banach spaces, I just mentioned Banach fixed point theorem. You're like, what does that have to do with anything? Well, okay, we have what's called the Picard-Lindelof theorem, which is named after Emile Picard and Ernst Lindelof. Go figure, right? But it's a pretty important theorem, which it gives a set of conditions under which an initial value problem, an ordinary differential equation initial value problem that is, has a unique solution. So when we're talking about real analysis as a branch of mathematics, you do classic Newton's derivatives, differentiation, integrals, you build up to the fundamental theorem of calculus, And, you know, historically after Newton and Leibniz, you get guys like Weierstrass and all of them making everything rigorous. What do we mean by continuity and all that? And then the next step after that is, you know, tiptoeing into ordinary differential equations. And so I feel like Picard-Lindelof, when you're like, okay, this is how we're showing that we have the existence and uniqueness of a solution to an ordinary differential equation, you're like for sure in modern real analysis at this point. So, well, how do you solve, or not solve, how do you prove this theorem? So the existence arm of the theorem is solved by applying Banach's fixed point theorem. So the sought solution of the differential equation is expressed as a fixed point of a suitable integral operator on the space of continuous functions under the uniform norm. So you transform your initial value problem into an integral equation, and you use the Banach fixed point theorem to then show that that integral operator has a unique fixed point. And then you would have to continue on to prove the other arm of the Picard-Lindelof theorem, the uniqueness aspect, with something else which is called Gronwall's lemma, which I'm not going to get into. But that's just kind of a warm-up background of what is functional analysis, because then as we get into more and more topics, it's going to be more obvious that that's kind of the subject matter that is in the background or underlying these things, or that's the area for further study that the further study would be into, I guess. So anyways, section 63 of Differential Geometry by Erwin Kreyszig. Two main topics: isotropic lines and isothermal coordinates. So first, isotropic lines. In the geometry of quadratic forms, an isotropic line, or null line, is a line for which the quadratic form applied to the displacement vector between any pair of its points is zero. And a quadratic form is just a polynomial where all of the terms are of degree 2. So you could have ax squared plus bxy plus cy squared. An isotropic line occurs only with an isotropic quadratic form and never with a definite quadratic form. So a quadratic form over a field called F, let's say, is said to be isotropic if there is a non-zero vector on which the form evaluates to 0. Otherwise, it's a definite quadratic form. Continuing on, using complex geometry, Edmond Laguerre first suggested the existence of two isotropic lines through the point alpha beta that depend on the imaginary unit I, where the first isotropic line is y minus beta is equal to I times the quantity x minus alpha, closed quantity, and the second one is y minus beta is equal to negative I times the quantity x minus alpha, closed quantity. But before I dig into that any further, red flag, the name Edmond Laguerre, and we ask ourselves, where have we heard that name before? And I will tell you where I heard that before, and that is the Laguerre polynomials, which is a fancy French name that starts with the letter L, polynomials. We vaguely remember that these are orthogonal polynomials. What's the other one? There's also, oh my God, I just mind f***ed myself. I was literally just saying, oh, Laguerre polynomials, these are orthogonal polynomials named after a French guy whose name starts with the letter L, not to be confused with these other similar polynomials. And then I just blanked on that second one. me. Legendre, that's what it is. Legendre polynomials. I was like, it was literally, dude, that would have bothered me so much if I would not have been able to remember that. Okay, holy smokes. Okay, as I was saying, so we were reading from the Wikipedia page for isotropic lines, and we got the simple definition. That's cool. We kept reading on, and the first guy who, I guess, defined some isotropic lines was Edmond Laguerre, but we really remember Laguerre for his polynomials. And his polynomials come up in Sturm-Liouville theory. And you'll see why this is all stuff that I feel like I should talk about this time. Because keep in mind, at the end of section 62, okay, this is the last differential geometry reading stream episode now. Last episode was on conformal mapping of surfaces into a plane, and at the very end we have problem 62.1, which is where we're looking at isothermic coordinates on something called a surface of Liouville. Okay, and the isothermal stuff had not been introduced in this book yet. It's kind of just like it's all just like kind of vortexed together, right? So Joseph Liouville and Jacques-Charles François Sturm are the namesakes for so-called Sturm-Liouville theory, which is theory surrounding a very particular kind of differential equation. So it goes like this. You have a so-called regular Sturm-Liouville problem on a finite interval from A to B, including those endpoints A and B. And the PDE looks something like d dx of the quantity p of x times dy dx closed quantity plus q of x times y equals negative lambda times w of x. And so p, q, and w are all these coefficient functions, where specifically w is this special one that people call the weight function or the density function. And lambda is, of course, an eigenvalue, which I'll get to in a second. But we have these requirements that p, q, w, and p prime are all continuous on this finite interval from A to B of interest for the problem. We also require that p is positive, non-zero, w is positive, non-zero for all x in our interval of interest. And the problem has separated boundary conditions of the form alpha 1 times y of a plus alpha 2 times y prime of a equals 0, and beta 1 times y of b plus beta 2 times y prime of b is equal to 0, where alpha 1 and alpha 2, and similarly beta 1 and beta 2, are not both 0. So those are the boundary conditions. This is what we would call a quote-unquote regular Sturm-Liouville problem. And so the whole idea behind Sturm-Liouville theory then is to study the existence and asymptotic behavior of the eigenvalues and the corresponding qualitative theory of the eigenfunctions and their completeness in the function space involved here, which I will say are Hilbert spaces, right? So, you're starting to solve all these PDEs and you build up stuff in functional theory. Maybe you switch around the form of your problem and you have an integral, and then you're like, well, oops, now Riemann integrals, are not enough. What are you going to do? How are you going to do this integral if all you've got are Riemann's techniques? You're not going to. You need more techniques. That sort of is in my view, like the motivation for a lot of this modern rigorous math stuff, right? Okay. The goals of a Sturm-Liouville problem then are to find the eigenvalues lambda, again going back to the form of the problem, for which there exists a non-trivial solution, and for each eigenvalue lambda then find the corresponding eigenfunction, namely y equal to some function y of x. The terms eigenvalue and eigenvector are used because the solutions correspond to the eigenvalues and eigenfunctions of a Hermitian differential operator. You can look that up if you want to know the exact definition, in an appropriate Hilbert space of functions with inner product defined using the weight function. And the main result of Sturm-Liouville theory states that for any regular Sturm-Liouville problem, first, lambda 1, lambda 2, etc. are real and can be numbered, so that we have in increasing order lambda 1 is less than lambda 2, etc. through lambda n, tending on all less than infinity, right? In increasing order. Corresponding to each eigenvalue then, lambda n, is a unique up to a constant multiple, of course, eigenfunction, y of n, which is equal to some functional representation y of n in terms of x, say, with exactly n minus 1 zeros in the interval of interest, a to b, called the quote-unquote nth fundamental solution. Furthermore, we have that for any regular Sturm-Liouville problem, the normalized eigenfunctions y sub n form an orthonormal basis under the W-weighted inner product in the Hilbert space, namely of square integrable functions on the interval of interest from a to b with respect to the weight function w of x. That is, we have the inner product between y sub n and y sub m given by the integral from a to b of y sub n of x times y sub m of x times the weight function w of x dx equals the Kronecker delta sub nm. So keep in mind, we're still answering what's up with the Laguerre polynomials. So step one, we had a brief tour of Sturm-Liouville theory, because if you start off with the Sturm-Liouville equation, the second order differential equation of that particular form, given those functions p, q, the weight function w, and we have our eigenvalue parameters and eigenfunctions associated with those, and so on and so forth. Then step two, the Laguerre polynomials, capital L sub n, say, of x are solutions to a particular Sturm-Liouville problem. Specifically, if we have d dx of the quantity x times e to the negative x, then times dy dx, closed quantity, plus lambda times e to the negative x times y equals 0. So namely, we have a Sturm-Liouville problem where the function p is x times e to the negative x, our weight function is e to the negative x, and we're just looking at the eigenvalues of natural numbers. We could also rewrite this Sturm-Liouville form problem in, I guess you could say, like conventional form, where we have x times d squared y dx squared plus the quantity 1 minus x closed quantity times dy dx plus n times y equals 0. So the Laguerre polynomials are solutions to this particular second order differential equation form. So I'm going to bring this yet again one step further, and we're going to mention what is called Rodrigues' formula, which is from Benjamin Olinde Rodrigues, who was, in addition to being a French mathematician, he was also a French banker, and he also was mentioned recently In section 59, we had theorem 59.1 from this man, Olinde Rodrigues, where we have at any point of a surface, capital S, the absolute value of the Gaussian curvature K of S is equal to the quotient of the element of area dA star of the spherical image of S and of the corresponding element of area dA of S. But we also heard from him earlier in section 45 when we were looking at the formulae of Weingarten and Gauss, and we had just gotten exposed to the formulae of Weingarten, and we got this representation for a normal vector on a surface in terms of coefficients of the first and second fundamental forms and, you know, whatever vector to the point on the surface of interest we're looking at. And then we got this so-called formulae of O. Rodrigues. So this is Olinde Rodriguez's own formula, the whole x sub alpha vector plus capital R sub alpha times vector n sub alpha equals 0 vector, where capital R sub alpha is obviously radius of curvature, being that it's the reciprocal of kappa sub alpha, which is curvature, and alpha can be 1 or 2. But that is Olinde Rodrigues as we have seen him in differential geometry. But I would say most people, especially engineers, right, have probably heard of Rodrigues, if at all, from Rodrigues' formula, which provides an explicit expression to obtain the Laguerre polynomials, which is that we have capital L sub n of x is equal to e to the x over n factorial, then times dn dxn of the quantity x to the n times e to the negative x closed quantity. And this makes sense because Rodrigues' formula is a common feature in Sturm-Liouville theory. It provides a systematic way to generate orthogonal polynomial solutions for specific Sturm-Liouville problems, including other polynomial families. For example, Hermite, Legendre, and Chebyshev polynomials. So there you go. It crawls out of the depths of the dust and the cobwebs of your memory. Laguerre polynomials, orthonormal. We have this basis for some space that maybe we're interested in for solving PDEs and all this whatnot. And you're like, ooh, Laguerre polynomials? Sounds similar to Legendre polynomials. Well, good thing, thanks to Rodrigues' formula, you can manipulate it a little bit and you can get all this stuff out. I'm not going to go over that, but moving on. Each family of orthogonal polynomials has a weight function and differential equation that fit the Sturm-Liouville framework. Isn't that fantastic? So yeah, I've kind of alluded to this, but we might as well say a little something specific about orthogonality and completeness. So the solutions to a Sturm-Liouville problem form an orthogonal set of functions with respect to the weight function w of x. For the Laguerre polynomials, capital L sub n of x, they are orthogonal on the interval 0 to infinity, including 0, with respect to the weight w of x is equal to e to the negative x. Namely, we have the integral from 0 to infinity of the product of Laguerre polynomials m and n, so we have namely the integral of capital L sub m of x times capital L sub n of x, then times e to the negative x dx is equal to 0, for, of course, m non-equal to n. So we're not multiplying the same Laguerre polynomial with itself in this integral. So this orthogonality property is a direct consequence of the Sturm-Liouville theory and ensures that Laguerre polynomials can form a complete basis in the space of square integrable functions on 0 to infinity inclusive of 0 with respect to e to the negative x. So we just kind of got blasted with Laguerre polynomials, and now we can return back to isotropic lines and we say, wow, this guy Edmond Laguerre, he was really up to something useful, that is. So among making his polynomials, he came up with these first isotropic lines, and maybe we can understand why nobody really remembers a lot about the first isotropic lines. But when he got these, and they involved complex numbers, okay, good for this guy, he interpreted them as geodesics, and thankfully for us, that is a key word. So that justifies reading on. An essential property of isotropic lines, and which can be used to define them, is the following. The distance between any 2 points of an isotropic line situated at a finite distance in the plane is 0. In other terms, these lines satisfy the differential equation ds squared is equal to 0, which we have seen all this before. On an arbitrary surface, one can study curves that satisfy this differential equation. These curves are the geodesic lines of the surface, and we also call them isotropic lines. Yeah, so for those of you who don't remember, a geodesic is like if you have a surface and between 2 points you have a rubber band. So, right, if you had a rubber band on a sphere as opposed to a chord that's just like cutting through it. And we also see that differential equation ds squared equals 0 in the study of geodesics. Whoops. Another interesting point here, in projective geometry, the isotropic lines are the ones passing through the circular points at infinity. So we had a nice rant tangent breakdown of some of that stuff 2 episodes ago. And another little bonus here, surprise, surprise, we are reading about differential geometry and something about relativity comes up. Isotropic lines have been used in cosmological writing to carry light. For example, in a mathematical encyclopedia, light consists of photons. The world line of a zero rest mass, such as a non-quantum model of a photon and other elementary particles of mass 0, is an isotropic line. For isotropic lines through the origin, a particular point is a null vector, and the collection of all such isotropic lines forms the light cone at the origin. So yeah, we have seen talk of this before. Light, world lines, interpretations of propagation of light and electromagnetic waves as geodesics and all this kind of stuff. And so we can really appreciate that we're getting terminology that has a real world application. You know what I mean? So the other topic in upcoming section 63 is isothermal coordinates. And it's just another type of coordinate system. The last thing I'll say is when I go through on isotropic lines, we can refer back to the end of section 60 where we had that summary table looking at different types of coordinate curves and what the values of different coefficients of the first and second fundamental forms would be, because when certain coefficients are 0, then we know that we're dealing with these certain special types of coordinate curves, right? But up to that point in section 60, we had only gone over orthogonal conjugate, lines of curvature, and asymptotic type coordinate curves. We had not yet gone over isotropic curves. We're about to, but that was already in that table. So don't forget, after absorbing in all this stuff in section 63, that we can contrast that with a lot of the stuff that has been in previous sections anyways. So the other thing, isothermal coordinates, I guess, we haven't even read straight up what's in here yet, but we can define this from Wikipedia. Isothermal coordinates on a Riemannian manifold are local coordinates where the metric is conformal to the Euclidean metric. That is, in isothermal coordinates, the Riemannian manifold locally has the form g equal to phi of dx1 squared plus etc. through dxn squared, where phi is a positive smooth function. And the notion of isothermal coordinates was first introduced by Gauss. We should all go and check out from the library Disquisitiones Generalis circa superficies curvas when we get done with this, maybe or not. Continuing on, the existence of isothermal coordinates on a smooth 2D Riemannian manifold is a corollary of the standard local solvability result in the analysis of elliptic PDEs. All right, so that's to kind of give foreshadowing for section 63. What about section 64, which is on the Bergman metric, where we're going to be reading the work of young Erwin Kreyszig when he was at Stanford in the early to mid 50s with this older guy, Stefan Bergman, working around him. What's that all about? Well, first we're going to need to know what a kernel is in the context that we're talking about. So do I mean a kernel as like the Linux kernel? Like, are we talking about Linux kernel development? Talking about operating system calls and, you know, drivers and all that stuff? No. We're in math land. Are we talking about kernel as like invertible matrix theorem, where matrix is invertible if and only if the kernel is trivial only, which is basically another way of saying that the only solution of ax equals 0 is the 0 vector, trivial vector? No, that is not the kind of kernel we're talking about here. We are talking about a kernel which is similar to an inner product, right? I've been talking about an inner product a lot with this whole Hilbert space, Banach space, function space. Well, a kernel is like a similarity measure defined on points in some set. So we have this function k of x and y for x and y being members of some set S, where we've defined it so that k of x and y is large when x and y are similar, and k of x and y is going to be small if they're dissimilar. So it is kind of analogous to an inner product, right? If you have two vectors and they're really similar, close together, you're going to have a larger inner product. If they're orthogonal, it's 0, right? So the idea of the kernel is analogous to an inner product in this way. So a fun fact about it is that if a symmetric kernel is positive definite, then it is essentially the same as an inner product. And this type of kernel is the kind of kernel used in kernel SVM. So all you AI engineers out there support vector machine. It's also kernel PCA, kernel principal component analysis. And it's also the same as kernel Fisher discriminant analysis, okay? That's the kind of kernel we are talking about when we have a Bergman kernel now. So specifically, a Bergman kernel is what's called the reproducing kernel for the Hilbert space of all square integrable holomorphic functions on a domain capital D, which is a subset of n-dimensional complex space. And so I threw this term out there, the reproducing kernel for the Hilbert space. What does that mean? A reproducing kernel for a Hilbert space is a Hilbert space of functions in which point evaluation is a continuous linear functional. That is, a Hilbert space H of functions from set X to the real numbers or complex numbers is a reproducing kernel of a Hilbert space H of functions from a set, let's say, X to the real numbers or complex numbers, is a reproducing kernel for the Hilbert space if for each X, which is a member of the set capital X, there exists a function capital K sub x, which is in that Hilbert space H, such that for all functions in that Hilbert space, the inner product of f and k sub x is equal to f of x. And so this capital K sub x, the reproducing kernel, reproduces the value of f at x via the inner product. That's a mouthful, and that's what the Bergman kernel is. I don't know if that helps you, but the Bergman metric here is where we have a Hermitian metric that can be defined on certain types of complex manifold, and it is derived from the Bergman kernel. And when I say a Hermitian metric, it's a metric on what would be just a complex analog of a Riemannian manifold, okay, which is just really, a really dolled up version of a surface if you really think about it that way. So more specifically, let capital G be a subset of n-dimensional complex numbers, be a domain, and let capital K of Z and W be the Bergman kernel on this domain capital G. Then we define a Hermitian metric on the complex tangent bundle by G sub ij of Z, which is denoted by partial squared partial Z sub I partial Zj conjugate of the logarithm of K of Z and Z for all of these Z which are members of the domain capital G. Then, after defining this Hermitian metric, then the length of a tangent vector xi in this tangent bundle is given by the magnitude of xi sub B and Z is denoted by the square root of the sum from the indices I and j equal to 1 to n of G sub ij of Z times xi sub I times xi sub j conjugate. This metric is called the Bergman metric on capital G. So hopefully that warms you up for what is to come here now. So now we are finally going to read directly from Differential Geometry by Erwin Kreyszig. And I've mentioned this in a few of the recent videos. There are pages missing from the PDF that I originally had been reading in like the first 20 or so episodes. These are like the hardest hitting sections, I would say, so far, and I could imagine why someone scanning this might accidentally, they scanned the whole book, but then they really wanted these, sections out of section 60 through 65, and then they deleted that out of their master copy, and then we all get the shortened version without it. But there's only one page missing out of what we're going to read today, so we're back to the PDF. Section 63, Isotropic Curves and Isothermic Coordinates. We confine ourselves to real geometric objects and consequently, in general, also to real functions of real variables. Nevertheless, it is sometimes advantageous to introduce complex variables as a tool for the investigation of real surfaces, that is, to regard the real Euclidean space as being embedded in a complex Euclidean space in which the Cartesian coordinates x sub j are complex numbers. This can be seen from this section, for which refer also section 83. A real vector function x of t, where t is a real variable, represents a real curve in space R3, provided certain conditions stated in section 6 are satisfied. We now assume that the components x sub I of t of the vector x of t are complex analytic functions of a complex variable t equals t1 plus I times t2, defined in a certain domain capital D of the complex t plane. Capital D is assumed to be the same for all three of those functions. Since t now depends on two real variables, t1 and t2, The vector function x of t represents a geometric configuration of infinity squared points. This configuration is called a complex curve or imaginary curve. A curve is said to be an isotropic curve or minimal curve if the length of the arc between any two different points of the curve is 0. Hence, a curve is isotropic if and only if ds squared is equal to 0 for when x prime is non-zero. Because of theorem 28.1, namely that at regular points of a surface the first fundamental form is positive definite, the previously given equation ds squared equals 0 cannot have real solutions, but has two conjugate complex ones. Isotropic curves are therefore always complex curves. Isotropic curves were first considered by Jean-Victor Poncelet, who, as it turns out, was the commanding general of L'École Polytechnique, and later especially by Sophus Lie, who, if you don't know who Sophus Lie is, you probably will see something that is named after him. He was the doctoral advisor of Élie Cartan, who is the father of Henri Cartan. And I'm going to pull this other book out here. We've got Introduction to Smooth Manifolds here. So some would say that this is like a more serious next level up, mathematicians only differential geometry book, okay? But if you look at the table of contents of this guy, Chapter 7, Lie groups, Lie subgroups. Chapter 8, Lie brackets, Lie algebra. Chapter 9, Lie derivatives. Chapter 19, Lie subalgebras and Lie subgroups. Lie correspondence. So obviously this guy Sophus Lie is not messing around. But as we know, okay, this says isotropic curves were first introduced by Poncelet and later especially by Lie. We have from Wikipedia, what about our boy Edmund Laguerre, okay? The first fundamental form can be represented as a product of two conjugate complex factors. That is, ds squared equals quantity, square root of g sub 1, 1, then times du1 plus 1 over the square root of g sub 1, 1, then times the quantity g sub 1, 2 plus I times the square root of g closed quantity, then times du2 closed quantity, and then times another quantity, square root of g sub 1, 1, then times du1 plus 1 over the square root of g sub 1, 1, then times the quantity g sub 1, 2 minus I times the square root of g closed quantity, then times du2 close outer quantity. For the expressions in square brackets, integrating factors can be found. If a sub 1 of u1 and u2 and a sub 2 of u1 and u2 are real functions of u1 and u2, and if a1 plus I times a2 is an integrating factor for the first bracket in the previously given relation for ds squared, then a1 minus I times a2 is an integrating factor for the second one since the two expressions are conjugate. Hence, there exist two functions, u tilde 1 of u1 and u2 and u2 tilde of u1 and u2 such that du1 tilde is equal to the quantity a1 plus I times a2 closed quantity then times large square bracket quantity square root of g sub 1, 1 then times du1 plus 1 over the square root of g sub 1, 1 then times g sub 1, 2 plus I times the square root of g closed quantity then times du2 close larger outer square bracket quantity. And also, du2 tilde is equal to the quantity a1 minus I times a2 closed quantity, then times larger outer square bracket quantity, the square root of g sub 1, 1 times du1 plus 1 over the square root of g sub 1, 1, then times the quantity g sub 1, 2 minus I times the square root of g closed quantity, then times du2 close large outer square bracket quantity. And the two families of isotropic curves on the surface, capital S under consideration, are the curves u1 tilde equal to a constant and u2 tilde equal to a constant. Consequently, by means of the transformation u alpha tilde equal to the function u alpha tilde in terms of u1 and u2, where alpha is equal to 1 or 2, the isotropic curves can be introduced as coordinate curves on S. By comparing the previously given relations for ds squared, du1 tilde, and du2 tilde, we find that the first fundamental form then becomes ds squared is equal to 1 over the denominator of a1 squared plus a2 squared, then times the product of du1 tilde and du2 tilde. We can now find isothermic coordinates on the surface capital S in the following simple manner. From the previously given relations for du1 tilde and du2 tilde, we see that u1 tilde and u2 tilde are conjugate. That is, u1 tilde and u2 tilde are of the form u1 tilde is equal to v1 plus I v2, and u2 tilde is equal to v1 minus I v2, where v1 and v2 are real functions of u1 and u2. Consequently, du1 tilde is equal to dv1 plus I dv2, and du2 tilde is equal to dv1 minus I times dv2. And the corresponding first fundamental form is given by the expression ds squared is equal to 1 over the denominator of a1 squared plus a2 squared, then times the quantity dv1 squared plus dv2 squared. That is, by means of the transformation v alpha given by a function v alpha in terms of u1 and u2, where alpha is 1 or 2, isothermic coordinates are introduced on the surface capital S. Since v1 and v2 are real functions of u1 and u2, the curves where v alpha is equal to a constant, where alpha can be 1 or 2, are real curves. Problem 63.1. Determine the isotropic curves of the unit sphere. The solution is as follows. If we choose the representation where the vector x in terms of u1 and u2 is given entry-wise by the cosine of u1 times the cosine of u2, then the cosine of u1 times the sine of u2, then the sine of u1, we have that ds squared is equal to du1 squared plus the cosine squared of u1, then times du2 squared, which is equal to the product of first the quantity du1 plus I times cosine u1, then times du2, closed quantity, times then the second quantity du1 minus I times cosine of u1, then times du2, closed second quantity. And the differential equations of the isotropic curves are du1 plus I times cosine u1 times then du2 is equal to 0, and du1 minus I times cosine u1 then times du2 is equal to 0. The function, the secant of u1, is an integrating factor. We thus obtain that du1 tilde is equal to the secant of u1, then times du1 plus I times du2, and du2 tilde is equal to the secant of u1, then times du1 minus I times du2. And by integration, u1 tilde is equal to the log of the tangent of 1/2 u1 plus pi over 4, closed quantity, plus I times u2. And u2 tilde is equal to the log of the tangent of 1/2 u1 plus pi over 4, closed quantity, minus I times u2. The curves where u1 is equal to a constant and u2 is equal to a constant are the isotropic curves on the unit sphere. We may represent these curves in the form u1 star and u2 star are both equal to e to the plus or minus I u2, then times the tangent of 1/2 times u1 plus pi over 4, which is then equal to the quantity of cosine u2 plus or minus I times sine u2, closed quantity, times the tangent of u1 over 2 plus pi over 4, closed quantity, which then is equal to a constant. There's a lot of trig identities and stuff like that going on in between lines here, so just be aware of that. Then the square root of u1 star times u2 star is equal to the tangent of 1/2 u1 plus pi over 4 and negative I times a fraction with a numerator of u1 star minus u2 star all over a denominator of u1 star plus u2 star is all equal to tangent of u2, or the sine of u1 is equal to numerator of u1 star times u2 star minus 1 over the denominator of u1 star times u2 star plus 1, and cosine of u1 is equal to a numerator of 2 times the square root of quantity u1 star times u2 star closed quantity all over a denominator of u1 star times u2 star plus 1, and sine of u2 is equal to negative I over 2 times the fraction with the numerator of u1 star minus u2 star over a denominator of the square root of the quantity u1 star times u2 star closed quantity. And finally, cosine of u2 is equal to 1/2 times the fraction with the numerator u1 star plus u2 star all over a denominator of the square root of the quantity u1 star times u2 star closed quantity. From this we obtain that the vector x in terms of now u1 star and u2 star, keep in mind at the beginning of the solution it was in terms of u1 and u2, so now it is equal to entry-wise u1 star plus u2 star over a denominator of u1 star times u2 star plus 1, and then negative I times the numerator u1 star minus u2 star all over the denominator u1 star times u2 star plus 1, and finally in the third entry a numerator of u1 star times u2 star minus 1 all over a denominator of u1 star times u2 star plus 1. This is a representation of the unit sphere. The coordinate curves u1 star equal to a constant and u2 star equal to a constant are the isotropic curves on this sphere. The ratio partial x1 partial u2 star to partial x2 partial u2 star to partial x3 partial u2 star is equal to the ratio of the quantity 1 minus u1 star squared closed quantity to I times the quantity 1 plus u1 star squared closed quantity to 2 times u1 star. This ratio is independent of u2 star. The ratio of partial x1 partial u1 star to partial x2 partial u1 star to partial x3 partial u1 star is equal to the quantity 1 minus u2 star squared closed quantity to the quantity negative I times the quantity 1 plus u2 star squared closed quantity to 2 times u2 star is independent of u1 star. Consequently, the isotropic curves of the unit sphere are imaginary straight lines. And as promised, we are now in section 64 on the Bergman metric. Conformal mapping plays an important role in function theory or functional analysis. The following basic theorem holds: every analytic function w equal to u plus I times v, which is equal to a function f of z, of a complex variable z equal to x plus I times y, maps the domain capital D of the z-plane, where f of z is defined onto the domain of the values of f of z in the w-plane, and this mapping is conformal at any point of the domain capital D at which df dz is non-zero. We now ask whether and in what manner it is possible to introduce in a domain of the complex plane a metric which is invariant with respect to conformal mappings. Quick side note, this is a criticism of this book that I've read online, which is where the metric is introduced right now. We're on page 200, but there has been pretty much no mention of metrics up to this point in the book. It's just kind of brought up here and assumed that everybody's cool with metrics. We just all know what's going on with that already. This problem yields an example of the relations between differential geometry and function theory. We will use the method of the Bergman kernel function as an essential tool in our investigation. This method has the advantage that it can be extended also to mappings which are defined by analytic functions of several complex variables. For details of the whole theory, see the book of Stefan Bergman called Kernel Function and Conformal Mapping, which was published in 1950 and which I'm actually going to skim at the end of this section for details on part of a proof. In what follows, this book will be referred to as BE. We denote by capital Q the kernel function, which is denoted by capital K in Bergman's book. We must first introduce some concepts which will enter into our investigation. A sequence, square bracket, capital phi sub alpha of z, close square bracket, of complex single-valued regular functions, capital phi sub alpha of z, of a complex variable z equal to x plus I times y, is called an orthonormal system with respect to a domain, capital B of the complex plane, if capital J of capital phi sub alpha and capital phi sub beta conjugate is equivalent to the double integral on the domain capital B of the integrand capital phi sub alpha of z times capital phi sub beta of z conjugate d lowercase omega, which is equal to Kronecker delta sub alpha beta, which is equal to 0 when alpha and beta are not equal, or 1 when alpha and beta are equal to each other. Where in the previously given double integral, d lowercase omega is equal to dx dy, and that is the element of area, and capital phi sub beta conjugate is the conjugate complex function of capital phi sub beta. In the following, we will always assume that the domain capital B is bounded. Instead of capital J of capital phi sub alpha and the conjugate of capital phi sub alpha, we write simply capital J of capital phi sub alpha. For a general theory of orthogonal systems, see also in the bibliography the works of Courant, Hilbert, and Jago. The set of all functions which are regular and single-valued in the domain capital B, and for which the Lebesgue integral, double integral on domain capital B of the magnitude of f of z, then squared, d omega, exists, will be denoted as the class L2 of B. If f of z is of this class, and if the sequence of functions capital phi sub alpha is an orthonormal system with respect to B, the numbers a sub alpha equal to capital J of f and capital phi sub alpha conjugate is equal to the double integral on B of f of z times capital phi sub alpha of z conjugate d omega are called the Fourier coefficients of f of z with respect to the sequence of functions capital phi sub alpha. It can be proved that the sum from the index alpha equals 1 to n of c sub alpha times capital phi sub alpha of z, where n is fixed, is the optimal approximation of f of z in the mean if and only if c sub alpha equals a sub alpha, where alpha is equal to 1 through n. That is, if and only if c sub alpha equals a sub alpha, the integral denoted by capital J of f minus the sum from alpha equals 1 to n of c sub alpha times capital phi sub alpha becomes minimum. An orthonormal system is called complete if the Parseval formula, namely where the sum from the index alpha equals 1 to infinity of the magnitude of a sub alpha squared is equal to capital J of f, holds. Hence, by means of a complete orthonormal system, the value of the integral, which was previously given, the capital J of f minus that sum, can be made arbitrarily small by increasing n, that is, by such a system f of z can be approximated in the mean to any degree of accuracy. The function capital Q sub b of z and t over bar, or t conjugate, is equal to the sum on the index alpha from 1 to infinity of capital phi sub alpha of z times the conjugate of capital phi sub alpha of t. Of the two complex variables z and t is called the kernel of the complete orthonormal system of the sequence of functions capital phi sub alpha. The series on the right-hand side of this function capital Q sub b of z and the conjugate of t converges in every closed subdomain b prime of b, The convergence is absolute and uniform in z for fixed t and is uniform in t for fixed z. And we reference the Bergman book here. It can be proved that capital Q sub b of z and the conjugate of t is independent of the special choice of the orthonormal system, but depends on the domain capital B only. Capital Q sub b of z and the conjugate of t is called the Bergman kernel function of the domain capital B. And now we have an example. The functions where we have capital phi sub alpha of z equals the square root of alpha over pi times z to the alpha minus 1 over r to the alpha, where alpha is 1, 2, etc., constitute a complete orthonormal system of the circular disk where the magnitude of z is less than r. The corresponding kernel function is of the form capital Q of z and t conjugate is equal to the sum on the index alpha from 1 to infinity of alpha over pi times the quantity z times t conjugate closed quantity to the alpha minus 1 all over r to the 2 alpha, which is then equal to r squared over the denominator of pi times the quantity r squared minus z times t conjugate closed quantity squared. The Bergman kernel function is related to the following minimum problem, which is in the Bergman book. Determine a function f of t regular in a bounded domain capital B, which at a fixed point t equal to z of b has the value 1, and for which the integral, which is the double integral on b of the magnitude of f of t squared, the magnitude is squared, not f of t, d omega is a minimum. The only function with those properties is f of t equals capital Q sub b of t and z conjugate all over capital Q sub b of z and z conjugate. The corresponding value of the integral previously given is 1 over capital Q sub b of z and z conjugate. The Bergman metric, which is invariant with respect to conformal mapping, is given by the first fundamental form. ds sub b squared is equal to capital Q sub b of z and z conjugate, then times the magnitude of dz squared, which is equal to capital Q sub b of z and z conjugate, then times the quantity dx squared plus dy squared. Since capital Q sub b of z and z conjugate is greater than 0, but not equal to 0, so it's positive, this form is positive definite. In order to prove the invariance property of that metric, we consider an arbitrary regular function, zeta equals xi plus I times nu equals capital F of z, which maps the domain B conformally and one-to-one onto a domain B prime of the zeta plane. The Bergman metric in B prime is determined by the first fundamental form, ds sub b squared equals capital Q sub b prime of zeta and zeta conjugate, then times the magnitude of d zeta squared, where capital Q sub beta prime of zeta and tau over bar denotes the Bergman kernel function of B prime. We have to prove that ds sub B prime squared is equal to ds sub B squared. Let z equals capital psi of zeta be the inverse of the mapping zeta equals capital F of z. If lowercase f of z is a function of class L2 of B, then f of capital psi of zeta then times d capital psi d zeta is a function of L2 of B prime, since we have that the double integral on B prime of the magnitude of f of capital psi of zeta, then the square of that magnitude, then times the magnitude of capital psi prime of zeta, then the square of that magnitude, d omega sub zeta is equal to the double integral on B of the magnitude of lowercase f of z, square of that magnitude, then times the magnitude of capital psi prime of zeta, then the square of that magnitude, then times the partial with respect to xi and nu over the partial with respect to x and y, then times d omega sub z is equal to the double integral on B of the magnitude of lowercase f of z, square of that magnitude, d omega sub lowercase z, where d omega sub zeta and d omega sub lowercase z are the elements of area of B prime and B respectively. If the sequence of functions capital phi sub alpha of z is a complete orthonormal system in B, then the sequence of functions capital psi sub alpha, where capital psi sub alpha is equal to capital phi sub alpha of capital psi of zeta, then times capital psi prime of zeta, where alpha is 1 through 2 through etc., is a complete orthonormal system in B prime. Furthermore, capital Q sub B prime of zeta and the conjugate of tau is equal to the sum on the index of alpha from 1 to infinity of capital psi sub alpha of zeta, then times the conjugate of capital psi sub alpha of tau, which is equal to the sum on the index alpha from 1 to infinity of capital phi sub alpha of capital psi of zeta, then times the conjugate of capital phi sub alpha of capital psi of tau, then times capital psi prime of zeta, then times the conjugate of psi prime of tau, which is equal to capital psi prime of zeta, then times the conjugate of capital psi prime of tau, then times the sum on the index alpha from 1 to infinity of capital phi sub alpha of z, then times the conjugate of capital phi sub alpha of t, which is equal to capital Q sub b of z and the conjugate of t times dz d zeta times the conjugate of dt d tau. Hence, ds sub beta prime squared of zeta is equal to capital Q sub b prime of zeta and the conjugate of zeta, then times the magnitude of d zeta squared, which is equal to capital Q sub b of z and the conjugate of z, then times the square of dz d zeta, then times the square of the magnitude of d zeta, which is equal to ds sub b squared of z. Wow, that was maybe some of the hardest stuff to read in this book so far out loud. I'm not gonna lie. The other hard stuff was like some of those crazy, like expanded out Jacobians and stuff in the tensor calculus section, but that was a mouthful right there. Theorem 64.1. Oof, here we go with the German. If B prime is a subdomain of a simply connected Schlicht domain B, then at every point of B prime, ds sub B prime is greater than or equal to ds sub B. The proof is as follows. 1 over capital Q sub B of z and the conjugate of z is the minimum value which the integral, namely the double integral on B of the magnitude squared of f of t d omega, can assume if all functions f of t, which are of class L2 of B, and have the value 1 at a fixed point t equals z of B are admitted. Hence, 1 over capital Q sub B prime of z and the conjugate of z is less than or equal to the double integral on B prime of the magnitude squared of capital Q sub B of t and the conjugate of z over capital Q sub B of z and the conjugate of z d omega, which then is less than or equal to the double integral on B of the magnitude squared of capital Q sub B of t and the conjugate of z all over capital Q sub B of z and the conjugate of z, then d omega, which is equal to 1 over capital Q sub B of z and the conjugate of z. And consequently, capital Q sub B of z and the conjugate of z is less than or equal to capital Q sub B prime of z and the conjugate of z. From this, we obtain the statement of theorem 64.1 by means of the Bergman metric. If, for instance, B is the interior of the unit circle, then according to the kernel function corresponding to the functions capital phi sub alpha of z given earlier in the quote-unquote example, then we have that ds sub b is equal to the magnitude of dz all over a denominator of the square root of pi times the quantity 1 minus the square root of the magnitude of z closed quantity. In consequence of the Riemann mapping theorem, B can be mapped conformally onto any simply connected subdomain B prime of the unit disk of the complex W plane. From theorem 64.1, we thus obtain the well-known classical result: the magnitude of dW over 1 minus the square of the magnitude of W is less than or equal to the magnitude of dz all over 1 minus the square of the magnitude of z. From the Bergman metric, we have in the case of the unit disk, g sub 1, 1 equals g sub 2, 2, which is equal to 1 over pi times the quantity 1 minus x squared minus y squared closed quantity squared. And g sub 1, 2 is equal to 0. Since the coordinates u1 equals x and u2 equals y are orthogonal, we may use the expanded out relation previously given in section 46 for the equation of Gauss. Like I said, that was one of the hardest things to read out loud, was that expansion of the equation of Gauss in section 46. Intense. And obtain, now, with that, partial x of the quantity 1 over the square root of g sub 1, 1, then times partial square root of g sub 2, 2 partial x closed quantity is equal to, in the numerator, 2 times the quantity 1 plus x squared minus y squared closed quantity all over the denominator 1 minus x squared minus y squared closed quantity squared, and partial y of the quantity 1 over the square root of g sub 2, 2, then times partial square root of g sub 1, 1 partial y closed quantity is equal to, in the numerator, 2 times the quantity 1 minus x squared plus y squared closed quantity all over a denominator of 1 minus x squared minus y squared, with the entire denominator then squared. Hence, capital K, Gaussian curvature, is equal to negative 4 pi. That is, with respect to the Bergman metric, the Gaussian curvature of that disk has a constant negative value. Since the Bergman metric is invariant with respect to conformal mapping, the above property of the Gaussian curvature holds for all simply connected Schlicht domains. In the case of multiply connected domains, the Gaussian curvature with respect to the Bergman metric is not constant. By using the above and further minimal properties of the Bergman kernel, we are able to find bounds for the value of the Gaussian curvature capital K at a point z of an arbitrary domain B. Let capital S sub capital R and capital S sub lowercase r be circular disks with radii capital R and lowercase r respectively. With centers at the point z of B under consideration, let capital S sub capital R contain B and B contains capital S sub lowercase r. Then we have negative 4 pi times the quantity capital R over lowercase r closed quantity to the fourth is less than or equal to capital K, Gaussian curvature, which is then less than or equal to negative 4 pi times the quantity lowercase r over capital R closed quantity to the fourth, where, of course, capital K denotes the Gaussian curvature at the point Z. The proof of this relation and further interesting properties of the invariant Bergman metric can be found in Bergman's book and in the original literature quoted therein, which is where I am going to conclude. We are going to open that up. All right. As we can see here, Kernel Function and Conformal Mapping by Stefan Bergman. And this book is dedicated to the memory of his sisters. It is not dedicated to Erwin Kreyszig. I repeat, this book is not dedicated. Okay. Anyways, I think this is chapter 4 that I'm looking for here, or chapter 3. Okay, 31. And right here. So basically, that relation that we were just looking at comes out of, we were looking at let B be an arbitrary domain. The curvature, lowercase c of z at the point z is given by c of z is equal to negative 2 times lambda superscript 1 subscript b, then squared over some other lambda, okay, some quotient of, I imagine, eigenvalues here, and we crunched through, and eventually after another page and a half, we get our relation here, negative 4 pi, and the, what? This curvature is bounded by reciprocals of these ratios of the radii to the fourth power and this negative 4 pi stuff. Anyways, this is going to be a long edit. Hopefully you guys have enjoyed that there were no neuropsychology rants this time. And as for the outfit, it's just a simple blue suit, white shirt, burgundy tie, no frills watch, no frills. See you guys in the next one. Peace.